We're going to look at what's called nuclear binding energy here. It turns out that the mass of a nucleus is actually less than the mass of the particles that make it up. For example, an alpha particle, we would expect the mass of the alpha particle to be equal to the mass of a neutron, the mass of two neutrons plus the mass of two protons, because those are the particles that make up an alpha particle. However, the mass of the alpha particle altogether is actually less than the sum of those two. Some of the mass from the particles, some of the mass from those particles, the nucleons, is converted into energy. And that energy is called the binding energy because it is contained within the bonds inside the nucleus. Right? So the energy is conserved, but again, mass is not. So if we want to find the binding energy, let's say we want to find the binding energy of an alpha particle. Well, there's just this mass that is converted into energy. Looking at that table in the appendix tells us that a helium nucleus, that it gives us for helium, it gives us a mass of 4.002603, but that is for a neutral helium atom, where an alpha particle is just a helium nucleus. So the alpha particle has a mass of that minus the two electrons that are part of the neutral atom. And the mass of the electron is something small, but if we punch that in, we get 4.00150584002. That's a lot of decimals. All right. Now the particles that make up an alpha particle are two protons and two neutrons. If we take 2 times the proton mass plus 2 times the neutron mass, that just gives us 4.031882. We can see there's a discrepancy here. And so if we find the change in mass, to find the change in mass, we just subtract those two. Take the 4.03, etc., minus the 4.00, etc., and we come out with a mass change of 0.0303 with more decimals atomic mass units. The binding energy then, that is how much mass is converted into energy, and so the binding energy is just delta M times C squared, which is 931.5 times this guy from up here, and that comes out to 28.295, etc., mega electron volts. So that's how we find binding energy. Now, if you look at page 1135 in your book, it gives a curve that looks something like this. I mean, this is kind of the general shape of it, and this is the binding energy per nucleon. So obviously, larger atoms are going to have more binding energy because they're larger. There are more nucleons. There are more bonds going on. But the binding energy per nucleon has this sort of shape where there is a maximum binding energy per nucleon, and then on either side of that maximum, the binding energy is less per nucleon. Okay, so if we take something over here and we split it into two things that are here, we'll have the same number of nucleons but more energy per nucleon, and so we get energy out of that, and that would be what we do with nuclear fission. And if we take something over here and we combine two of them into something bigger, we get more binding energy per nucleon, and so there's more energy floating around there, and that is nuclear fusion. Okay. Fission is splitting a big atom into two smaller atoms. To give you an idea of what's going on, the binding energy of uranium-235 it has a binding energy of about 7.5 mega electron volts per nucleon. And two atoms that are about half that size have binding energy of about 8.3 mega electron volts per nucleon. So the difference between these, obviously 0.8 mega electron volts per nucleon, is how much energy we get out when we split a uranium atom into two. Now, in uranium-235, there are 235 mega electron volt, or 235 nucleons. We multiply that by 0.8, we get that we come out with about 200 mega electron volts per atom of uranium split. Now that's a pretty large quantity of energy. For a point of reference, burning 1 gallon of gasoline, or burning a molecule of gasoline releases 2 electron volts. So obviously, fission gets you more energy per molecule, per atom. So fission is a more efficient way of producing energy than burning gasoline. Although there are certainly more spectacular dangers associated with fission than there is with gasoline. So what happens in a fission reaction is that you got your big uranium atom, and it gets hit by a neutron that's moving pretty slowly. Slow neutron. It hits the atom. It's absorbed, and the atom kind of starts wiggling around and then splits into two smaller atoms and another neutron or two or three. It's not necessarily known how many neutrons will go out, but there's an average of about 2.47 neutrons released. Okay. These neutrons can then hit other uranium atoms and cause them to fiss, which, believe it or not, is actually a verb, I think. And so then there's that chain reaction that happens. Now, there's a lot of energy being generated in each of these reactions. A nuclear bomb is just an uncontrolled chain reaction. So each atom that splits shoots out some neutrons, but two or three typically, and then two or three more atoms fission, and a bunch of energy is released. So a nuclear bomb is an uncontrolled chain reaction of nuclear fission occurring. Now in a power plant, of course, you don't want that to happen because then it will explode, and that is bad. But in a power plant, they try to control the reaction, only producing as much energy as can be productively converted to electrical energy. So typically, a few things are going on in a nuclear reactor. First off, there's some kind of moderator that slows down the neutrons because they have to be going relatively slowly in order to cause more fission to occur. There are also control rods that absorb neutrons. Typically, they're made of cadmium because cadmium is good at absorbing neutrons. But the purpose of the control rods is to regulate the rate of reaction. So if we put our control rods all the way in, they absorb basically all the neutrons, and so the reaction stops. If they are all out, then we get the runaway chain reaction. We get our kaboom. So ideally, or somewhere in between those, that's where you want to run a nuclear power plant. You don't want, if your rods are absorbing all the neutrons, there's no reaction. You're not getting any energy. If none of the rods are in there, then you get the runaway chain reaction and your power plant explodes, like Chernobyl. So you want to be somewhere in between, and that is what is called the critical the critical reaction rate, or critical something or other. The critical reaction rate, they try to make it so that there is about 1 neutron that is not being absorbed, that is continuing the reaction. So there's the same amount reacting at any given time. You have a fairly consistent energy output, and we're able to productively convert that into electrical energy. So that's how nuclear fission works. Fusion is combining 2 lighter nuclei, typically hydrogen, combined into heavier nuclei. All right. It requires a large amount of energy to start the reaction, because you have to overcome the Coulomb force in order to push the nuclei close enough together for the strong force to kick in and be stronger than the Coulomb force. As you probably know, stars produce their energy using nuclear fusion. They have a lot of hydrogen in them, and that hydrogen is fused into helium, generally speaking. And sometimes hydrogen and helium fuse to make lithium. But the hydrogen to helium is the predominant reaction that's going on in stars. Now, and stars, of course, have lots of energy. They're very hot, and so they're able to keep this fusion reaction going. At the presently, the energy you have to put in in a lab to get nuclei to fuse, the energy you have to put in is greater than the energy you get out of the reaction. So it's not a practical means of getting energy currently. However, they're getting close to the break-even point on this, and I would guess that this nuclear fusion will become a viable source of energy within my lifetime, but I don't really know. But this fusion is something that's being looked into a lot, because what you need for fusion is you need a particular isotope of hydrogen called deuterium, and that isotope is readily available because it is common in seawater. And so we have a lot of reactants, I guess, that we would need to keep performing fusion reactions, and so it's something that is being investigated as a possible energy source for the future, even though currently it's really not practical to carry out.